Good afternoon. Good afternoon. Is it working?
Someplace.
Yeah. Is it working, Bob? Yes. Hello. Hello. Good afternoon. Welcome. Welcome. I'm Betty Slight, and I'm here to just sort of keep things going this afternoon. A couple of things before we begin. Housekeeping. Washrooms are at the very back to the left of the kitchen. The elevator. Did anyone need the elevator today? I didn't hear. So we won't worry about that. The fire exits. There's an exit here. The door you came into, and there's another exit at the back. If there was a fire alarm, please keep calm and just exit quietly out of here. Okay. We are in my Kiwi Key, the ancestral and unceded territory covered by the treaties of peace and friendship. We are all treaty people. Today we will welcome Mr. Richard Zurawski, and I'll tell you a little bit about him. Richard has a weekly science question and answer show on Q104 radio in Halifax, Q Files. He's been on air, he's been an on-air meteorologist and science reporter for CBC, CTV, Global TV, and Rogers Media. He was elected HRM, Halifax Municipality, Councillor for District 12 and served for 4 years between 2016 and 2020. He was also the Green Renewal Critic for the Green Party of Canada Shadow Cabinet. He's in the final stages of his PhD at Mount St. Vincent, specializing in climate change and the media. He also has a BSc in physics and an MA research in education. He has also been a lecturer at St. Mary's and Mount St. Vincent from 2011 to 2017. As a documentary filmmaker, he has produced, written, and hosted numerous science and history documentaries, broadcast domestically and abroad. He has syndicated 3 children's television series, Wonder Why, The Adventures of the Aftermath group, Math, M-A-T-H, and Wise Weather Wise. He has published 4 books. One was The Maritime Weather. The second is about climate change. The third about media in science. And his fourth, The Science Files, Questions and Answers from A to Z, is based on questions and answers of his online listeners. My work, or his work, sorry, to promote science and learning at all levels was rewarded in November 2013 with the Discovery Center's Science Champion Award. I'd like you to welcome Richard Zurawski.
Thank you. Okay.
You're taking that.
Okay.
And I'm not sure what you do with that.
I'm going to put this in my someplace here. There we go. All right. I hope that works. Are we all set? Okay. I'm really pleased to be here, first of all, to deliver this series of lectures. And climate change has been something I've been looking at now for more than 40 years. So it's been a real uphill battle, and it's really heartening to see a nice crowd like this out there. And hello to everyone out in the cyber world as well. In structuring this series of lectures, it's so easy to get trapped into the pestilence, death, and destruction mode of what we hear so much about relating to the climate crisis. And the way these lectures are going to be structured is to look at the weather, its relationship to the climate, what affects it, the physics that goes into it, the various chemistries that are involved in that, and then starting to look at the Earth's past, and then starting to look at what is expected to happen. And through that, we'll then start looking at what we can do to adapt to it and mitigate the effects of climate change. And right now, the climate is, I think we're experiencing something in climate change right now. This has been the driest April ever recorded in the Maritimes. We're down to 20% of our normal rainfall. It's supposed to be April showers bring May flowers. And unfortunately, that is not the case. So let me start out. There we go. Whoops. I guess it's not as quick as I am. So the IPCC, which is the Intergovernmental Panel on Climate Change, released its final report. There are no more reports coming out until 2030. So this report is a synthesis of the sixth assessment, and it came out, it says last week, but it came out about 6 weeks ago. The synthesis report is really looking at a worst case scenario. That is the tragedy of the climate crisis. We're now past the stage where we can expect the best case scenario or a middle case scenario. If we continue to do what we are doing, we are going to be looking at a worst case scenario. So we're going to be covering the current status, the trends, the future of climate change, the risks, the responses, and the near term. That's really what we're concerned about, because there are going to be some dramatic near-term effects. One of the things that just popped up this past week was an assessment on what's going on in the Pacific, the El Nino, La Nina phase, which we'll be talking about a little bit later. But it appears like we're going to be entering an El Nino phase, which is the release of warmth coming out of the Pacific Ocean. The Pacific Ocean is the largest body of water on the Earth and is the biggest weather effector. So what happens in the Pacific, surprisingly enough, will be affecting us as well. So this is important because we have so many things to do to be able to adjust to what's going on in the climate. We have technology which actually insulates us in Canada and the US and in Europe from many of the effects. We have air conditioning, we have the ability to extend our energy uses. Other parts of the world just don't have that. We had one of the warmest heat waves ever recorded in April. It happened this year in India. Temperatures approached 50 degrees Celsius. So more than 3 billion people are now highly vulnerable to climate change. We are not so much. We will not feel those effects the same way that people living in India, in southern China, Indochina, and large parts of Africa. And that leads to a lot of instabilities, which we will also be covering. 50, yes. Yeah. Well, 50 is something I've only experienced once. I did a talk a number of years ago in Al Ain in the Emirates, and they record routinely temperatures in 50, and it's just not functioning temperatures. And if you're looking at humidity, you're also looking at some really significant problems where people just can't be outside in those temperatures. So we're going to be looking at mitigation. How do we solve this climate crisis? And I am calling it not climate change, but climate crisis. And then adaptation, like there are ways that we can adapt. We can change our habits. We can change the things we do. And then we'll take a look at migration and how mitigation, adaptation will affect us as other people start to come here. Because if I had to live in one place of the world to be insulated from the changes of climate as much as you can be, the Maritimes is it. This is as good as it gets. Yes. So 6 lectures. Lecture 1 is basically what is the climate crisis? How did we get here? We'll look at stats and graphs and chemistry and physics, sort of an Al Gore summary, but updated. He delivered his talks 20 years ago. Lecture 2 is going to talk about paleoclimate. This is a really interesting part of the lecture series, what has happened in the Earth's past. And surprisingly enough, the Earth has been much warmer in the past than it is projected to be now. We had an event called the Paleocene-Eocene thermal max, where the temperature is actually 15 degrees Celsius on average warmer globally than it is right now. So we can adjust and we can survive to this, but the speed with which things are happening are the issue. Lecture 3 will begin with the mitigation. We'll look at the large picture, the governmental mitigations, the corporate mitigations, changing to electric cars, changing to various power systems, renewable energies, that sort of thing. Lecture 4 will be 2 hours on personal mitigation, what we can do personally to make life easier for ourselves and cushion the blow a bit. It's important to differentiate between what the government can do and what you can do as an individual. So much of it has been offloaded to make the individual feel that they have to do everything, and the governments have been lagging. And so we're talking municipal, provincial, and federal lagging. We were just talking about that a little bit earlier, how it seems when we talk about doing things, we're always about 10 years behind what we should be doing. Lecture 5 will be talking about adaptation, adjusting, and acclimatizing. You know, there's ocean level rises, more storms, frequency, building codes, that kind of thing. And then lecture 6 will be talking about a kind of a pet topic of mine, is where you get your information. Who do you trust anymore? It's really difficult not to get bogged down into delayers, deniers, all kinds of pushback against what the science is telling us. And what I'm going to be lecturing on is what has been presented by the scientists. It's not my opinion. I try to keep opinion out of it. What I'm going to be looking at is what the scientific studies tell us, the shortcomings of that, and what we can trust from those, how much we can elaborate from those particular studies. And so we'll go through that, and I won't do too much of that kind of thing because both your eyes and my eyes will start to glaze over when we take a look at all the ins and outs of the climate crisis. So those are the 6 lectures. I'm just going to stand up for a second here. So questions are welcome. I'll try to remember to repeat the questions as they come in. If you have a question, throw your hand up. If I don't see you, yell at me, kind of thing. It's difficult not to be polarized in this. There will be inevitably questions calling into, you know, is the climate crisis as bad, or is it actually happening? Or I saw a YouTube video the other day that said that it's a conspiracy kind of thing. So we'll field a few of those questions. I look at this as kind of a person-to-person thing. It's when we talk about climate crisis, it really is an individual thing, how we respond, how we vote, how we get our information, and what we trust and don't trust. So I'm going to try to point out where you can get your information and what your information is going to tell you about where we should be going. It's easy to get lost in the bad news, so I'm not going to try to bury you with the sky is falling. We already know that the sky is falling. Not enough rainfall, though. So that's sort of the overview. And we're also going to talk about money. That was a question that was put up a number of weeks ago about whether I'll be dealing with the influence of capitalism. I just noticed Joan. Hi, Joan. How are you? Joan's an old friend of mine, and I was told she was going to be attending, so now I have to be on my toes here. Good. I am going to be held to task. Okay, so what is the climate crisis? How did we get here? and the IPCC report. So we're going to do an overview of everything. So the climate crisis isn't just related to the atmosphere. It's related to the ecosphere, which consists of 5 large parts. So we're going to talk about the atmosphere, which is what we're living at the bottom of. We're at the bottom of an ocean of air. And surprisingly, we're the lobsters crawling along the bottom for the most part. We look up, half of all our atmosphere falls in under 18,000 feet. So about 3 miles up, you get half of that atmosphere. We have roughly 1 billion cubic miles of air in which we live. So 8 people and all of our activities, industrial, all the ecosystems have to live within that small little thin envelope that Carl Sagan called a pale blue planet. Then we're going to look at the oceans and water. If anything, in climate change, the oceans are probably the most important constituent. Water is an amazing substance. We live in sort of the triple point of water, where water can exist on the earth as a solid, a liquid, and a gas, and the transfer from state is what determines the climate and the weather. So this water tie-in is incredibly important. And we're going to be talking about the El Nino and La Nina phases as well, because that relates to the outgas or the outpouring of heat that the oceans have stored. Then we're going to look at crustal plates. The positioning of the continents where they are right now play an important part. In addition to that, we'll look at the biosphere. To give you an example of how powerful the biosphere is in our atmosphere, 20% roughly, give or take a percent, of the atmosphere is oxygen. And if all the oxygen were to disappear today, so we're talking 300 million cubic miles of oxygen, in 2,000 years, the biosphere would put all that oxygen back again. So all the little bugs and beasties that do photosynthesis, that do the transfer of carbon dioxide into energy and that kind of thing, anaerobes, they would all put the oxygen back. So they're very important as a feedback mechanism. And then we're going to talk about the cryosphere. That's not to do with anything that I'm going to do at the end of the lecture. It has to do with the frozen lands, the ice that we have. It's an incredibly important signature in the climate crisis. And the first part will run about an hour, and then we'll take a 10-minute break, and then we'll finish up with another hour. So we're going to concentrate on how we got here and the constituents. So the atmosphere extends roughly 100 kilometers upwards. It's not very thick at all. Once you get above 3 miles, it dissipates very, very quickly. At the level that airplanes fly, you're above 3/4 of all the atmosphere. So at about 250 millibars. And as a meteorologist, we are always concerned with the millibars because we can look at signatures that help us determine what the weather is. As I said, roughly 1 billion cubic miles of air is all we have. And we've got 8 people with all their industrial activity, plus everything else that has to live in that little. Think of yourself as sharing that little box of air, a mile by a mile, and everything with 8 other people, however they drive, however they work, plus all the animals have to share that. So it's not homogeneous. It's not the same stuff all the way to 100 kilometers. We have a number of layers. And from the bottom to the top, we have what's called the troposphere, the trope that we live in. That is roughly extending, give or take, in the tropics. It's higher than it is in the Arctic and Antarctic. It ebbs and flows depending on the temperature of the air. We know that when we heat the air up, it expands. When we cool it down, it contracts. And so the troposphere where we live is defined by the fact that there's water vapor in the trope. And water vapor is incredibly important for the transference of energy from the equator to the poles. And how it does that gives us the low pressure systems, the storms, all the weather that we experience, and also in general terms, the climate. So the troposphere is what we are really concerned about, but there's more of the atmosphere than just the trope. So what we have is stratosphere, which is where airplanes fly. It is notable in that there's no water vapor there at all. It's pretty much dry, bone dry. So everything that happens as it relates to water happens in the troposphere. That's where we get most of our clouds. Today we have that huge cirrostratus layer. That tells you where the boundary of the stratosphere is. Anytime you see cirrus clouds, you're boundarying the stratosphere. And then we've got the mesosphere, which is roughly the middle atmosphere, the thermosphere, which is where the atmosphere actually heats up. Some parts of the thermosphere, the temperature gets above 100,000 degrees Celsius. It's an amazing thing. But it is so rarefied, there's not a whole lot of energy associated with it. It's almost at a stage where you could touch it without getting burned because there are so few atoms impinging on you. And then we have the exosphere, which is the outer space region, which is where the space shuttle flies, and it bumps into a few molecules. And then we have the ionosphere, which is what we've been noticing. I don't know if anybody's gone out in the evening, but if you look outside, we've had some solar flares, and the ionosphere, which is generated by a magnetic field that the Earth puts out, actually protects us from the particles coming in from the sun generated by the prominences and solar flares. We've had an outgassing of solar flares on the sun, which is bumping into our atmosphere and giving us the aurora borealis, the northern lights, or the australis. So they've been really prominent and quite pretty. So let's begin with the troposphere. That's the lowest layer. It extends about 10 kilometers up. If you're still in the old system of measuring things, that's about 6 miles or so. We live in the bottom. All the weather occurs here. That's why we're concerned about it. And the clouds appear here as well. And water vapor is found in the troposphere, and it works its magic. It is actually transferring the energy from one part of the Earth to another. And that's basically how the troposphere works. And it's also, as far as temperature goes, the higher you go, the colder it gets. So that's why you've got snow on mountaintops, because it gets colder up there. And of course, if you're flying, very often they'll tell you the temperature outside, and the boundary of the stratosphere is about -50 to -70 degrees Celsius. So the higher you go, there's a lapse rate in the temperature, and there's also a lapse rate in the pressure. So when you go to mountaintops, if you're at roughly 10,000 feet, you're above a substantial portion, probably a third of the atmosphere. You get to 18,000 feet, while you're above half the atmosphere. So that's basically the troposphere. The stratosphere is the next layer. That's also where the ozone layer lives. Ozone is important to us. If I were to categorize gases in the atmosphere and their importance as far as the climate goes, 98 to 99% of the gases of the atmosphere right now play zero role in importance. Nitrogen is 78 to 79%, oxygen is 20-21%. And as far as its effect on the weather, and as far as its importance on climate, it's zero. The important ones are in minute amounts. And one of the minute amounts is the ozone layer. The ozone layer actually protects us because it has a predisposition for absorbing ultraviolet, A, B, and C, that comes in from the sun. And that we remember the ozone crisis, it must have been 40 years ago when we started noticing that chlorofluorocarbons that we were using for air conditioning was actually eating up the ozone layer. And because it's so rarefied in the stratosphere, it doesn't take much to eat up the ozone. Ozone is a particular bunch of oxygen that comes in triplets. It's O3, and it's highly reactive. And if you were to, even though it's oxygen, if you breathed a couple of airfuls of ozone, instead of O2, which is the oxygen, the molecular oxygen that we breathe, it would kill you. It would actually eat apart your lungs. And it's very, very reactive. We actually get fairly high ozone levels in most urban areas, especially when we get smog. And we can also smell it during a thunderstorm with a lightning strike. So you get that particular pungent smell if you're close to a lightning strike. You don't want to get too close to it. However, you get that smell, that's the ozone that you're smelling. And it's a significant portion of smog as well. So the importance of the stratosphere is that it is not the troposphere and that it does contain the ozone layer, which is very important to us. For those of us that have a predisposition to cataracts, the ozone layer and its health actually impinges on getting cataracts. If you have a weakening in the ozone layer, we have a greater predisposition to getting cataracts. And at the height of the ozone layer in southern Chile and Argentina, the Antarctic ozone hole was big enough that it actually covered the southern areas of Chile and Argentina, and they started noticing some of the sheep were going blind. Because there was so much ultraviolet coming in. Ultraviolet's not good for you. Also makes your skin old, which we all have. And it really leads to various types of cancer, which I had on my nose. That's probably from sticking it in the wrong places and talking about climate change. So it's also less turbulent. You'll notice that in the troposphere with all the water vapor, there's a great deal of turbulence. We get storms, we get hurricanes, we get typhoons, we get cyclones, that kind of thing because of water vapor. Doesn't exist in the stratosphere. So we don't get that kind of thing. And it's very, very calm up there. Not much of it though. So the mesosphere is above the stratosphere, and it's kind of a rough middle atmosphere. And we're constantly redefining what the atmosphere looks like. So when we talk about climate change, it's really important to understand the different layers because they interact with each other. And they also tell us how in the interaction, what we can expect to happen as things start to change. You get more heat in the troposphere, it pushes up higher. It also changes the structure of the stratosphere because more oxygen will bleed into it, and also more water vapor will bleed into it. And hopefully you'll wind up with a healing of the ozone layer. So it extends, roughly 85 kilometers above our heads, 53 miles or so, which is higher than all of us have been, with the exception of the 60s. Sorry for that. I have a terrible sense of humor. Most meteors that come into the Earth's atmosphere is incredibly important on a number of levels, not just climate change, but it also, and protecting us from the sun, it also burns up a lot of the rocks that come in our way. And anytime, I guess it was just the Lyrids we had a couple of days ago, it was we had a clear sky and we were able to see in the constellation Lyre. It has nothing to do with meteorology or me, but Lyre for the ancient musical instrument, and the principal star is Vega. So at midnight, it would have been pretty much over your head, straight over your head. You could be noticing the meteors coming in, striking the mesosphere and burning up, and keeping us from being hit by little meteorites as they strike the Earth. We get indications that that happens from time to time. Anything bigger than a boulder will probably wind up hitting the Earth. This is a pretty cold place. The mesosphere goes down to about minus 90 degrees Celsius, sort of outer space. This is near the top of the layer, and it's far too thin to breathe. If you look at the highest reaching hydrogen balloons that we put up there, I'm trying to think of the name of the guy who jumped out of a hydrogen balloon. He was at the very top of the stratosphere, very close to the mesosphere. Yeah, Felix Baumgartner. That's it. Thank you. Yeah, I don't recommend jumping out of hydrogen balloons to go through the atmosphere. he got up there. The temperature was very cold, and his speed got upwards. I think he broke the sound barrier coming down because there was so little atmosphere. And he also got into a kind of a spin that could be very dangerous. So if you're at that level, you're 99% above all of the atmosphere of the Earth. And the thermosphere, this is where we start noticing high energy X-rays and UV radiation from the sun being absorbed in addition to the ozone layer. So the X-rays are also important. Like when we start looking at other planets in our solar system, not our solar system, but extrasolar system through the James Webb and the Hubble telescope, we're looking for planets that are around stable stars, and we're finding that a lot of the planets that are Earth-sized or super Earth-sized orbit red dwarf stars, and they're really reactive stars, and they're very close to them, and they're full of X-rays. So they have a lot of solar flares, and they send out X-rays. So what the sun sends out that is intercepted by our atmosphere actually sets off the X-rays. So we wind up with particles coming off the sun. They strike the upper atmosphere, and in the striking of it, it acts like a cyclotron. It's the same thing as the Fermi Institute cyclotron, where they spin protons around and electrons and smash them into things, and then they look at the detritus that comes off that. So at the top of the thermosphere, which extends up to 621 miles or 600 miles above the atmosphere, the temperature can approach 2,000 degrees. And in some cases, if you look at the bell curve and the black body radiation curve at that point, some of the temperatures can be as high as 100,000 degrees. So I don't recommend it. So then we get to the exosphere, and it is really, it extends to about 120,000 miles, so about halfway to the moon. And it's just the leftover of the atmosphere. There's certain gases that break up when the sun's energy comes out of the flares. So the particulates strike the upper atmosphere. It ionizes a lot of that. And I'm just trying to think here. The leaking out of hydrogen and helium happens here, and the breaking apart of oxygen. So we start losing some of our atmosphere at this place because of the energy coming off the sun. It receives a fair amount of energy, and we need the addition of planetary, interplanetary bodies like comets and meteors, that kind of thing, where the Earth picks up extra mass, which it goes into the atmosphere. So that's basically the structure of what we're talking about. And the ionosphere isn't really a layer. It's where the radiation and particulate matter from the sun strike to create a plasma. Ions are just basically a form of matter. They're not solid, liquid, or gaseous. They're highly charged particles, and the ionosphere is where it lives. And these ions are something that we have to look out for when we send spaceships out. We have to insulate them. And we only discovered them when we started looking at the space race. So the Van Allen radiation belts, that's part of we discovered those when we were sending rockets up. So what we're concerned about is basically the trace gases. So the 1%ers. We're not that interested in nitrogen. That is a paleo gas that's been with the Earth for over 4 billion years. Oxygen has been with us in varying amounts for the last 3 billion years. So nitrogen is the oldest, and it makes up almost 4/5 of the Earth's atmosphere. Oxygen we really need to metabolize, and it's been around for about 3 billion years. All the other ones, water has been around. It is actually as old as the nitrogen. So a lot of the stuff that formed the Earth had water in it, various ice that contributed to the oceans. And as we look into our solar system, we find that just about every moon has water deposits. We look at the Jupiter's moons, all 4 of the Galilean have significant oceans, more water on Europa than on the Earth, even though Europa is roughly the size of the moon. And carbon dioxide, that's been around for a long time as well. Methane is been around as long as oxygen and a little bit more, because the anaerobic biota that lived on the Earth in our paleo past produced methane, and methane is a substantial greenhouse gas, and then there are other trace gases. So the gases we're going to be concerned about are water vapor, carbon dioxide, and methane as far as climate change is concerned. And all of those are part of the troposphere. So nitrogen and oxygen don't play much of a role. The greenhouse gases that we're going to be talking about are the 3 that I just mentioned, and they're less than 1% of the total constituent of the atmosphere. So water vapor, and this graph, there we go, is showing you the water vapor, carbon dioxide, oxygen, ozone, where it occurs, and how it absorbs, how we notice it. And you look at water vapor and it absorbs a lot of heat. So once you get water vapor in the troposphere, the form of clouds, the changeover, water vapor is very, very important. It's probably the principal greenhouse gas in terms of what we're experiencing. And it varies depending on the temperature. If the temperature of the Earth goes up, we wind up with more water vapor in the atmosphere. That increases the temperature yet again. It becomes a feedback mechanism. And that's called a runaway effect, which is something that we'd like to avoid. If you want to look at a runaway greenhouse effect, we have a planet that actually exhibits that. And there's a bit of a story attached to that. When I was an undergraduate, way back when in the Precambrian times, my atmospheric physics prof came and he said, I want to talk about runaway greenhouse effect. And I thought he was going to talk about Venus. Because Venus, at one point, when the sun was much dimmer than it is now, the evidence is telling us that it actually had oceans and had a climate that was very similar to the Earth. But as the temperature increased, the oceans boiled off. And the temperature now on Venus is hotter than it is on the sun side of Mercury, approaching 800 degrees Fahrenheit, enough to melt lead. Carbon dioxide has been around for a long time. In the Earth's distance past, its second atmosphere was probably about 90% carbon dioxide, which allowed it to heat up enough because the Earth received only about 65 to 70% of the insolation from the sun. That's the radiation coming in because the sun was much dimmer in the distant past, 4 billion years ago. Methane is, for the most part, a biological input, although methane does form in other ways, other chemical ways. And then nitrogen oxides. Nitrogen does play a small role in its interface with the ground. How the greenhouse effect works. It doesn't work the way most people think it does. It's not the heat of the sun coming in. What it is the light of the sun comes in and strikes the Earth and is translated into infrared radiation. And that infrared radiation strikes the ocean, strikes the ground. It goes through the atmosphere for the most part. And it is then translated into infrared radiation, which is heat. And so depending on the chemistry, which we are now changing, it creates a warmer temperature on the Earth. If we were to delete the atmosphere, the temperature of the Earth would be between 15 and 30 degrees Celsius colder than it is now. And so that trapping effect by the atmosphere, by these gases, by water vapor, by carbon dioxide, by the methane, gives us the heat, and it stays in. With the water vapor trapping so much of the heat, it's basically, consider it to be black as far as its effect on re-radiating the heat outside the Earth. So it keeps it in. So you can see the heat budget that's going there. So the greenhouse effect depends on the average temperature of the Earth, and it depends on the chemical makeup of the various greenhouse gases, in short. And then we have something else called albedo. And this is where the cryosphere comes in. And the cryosphere, as I mentioned, is the areas where we have ice. And the largest area in aerial extent is not Antarctica, it's the Arctic because of the ocean. And it has a lot of ice floating in it, and it's roughly about 50% larger, probably 6 to 7 million square miles at its maximum extent. And so that's white area. So as soon as the light of the sun comes in, it's reflected back again. And because it's cold, there's very little water vapor in it. So it's only carbon dioxide, and there's very little methane because it caps a lot of the bacterial movement. So it's important that we have a cryosphere to keep the Earth cool. Otherwise, we heat the average temperature of the Earth up, and we wind up with the runaway climate change. So it gives you the various albedos. Snow is very high, cumulus clouds very high, and then you get all the way down to pavement and buildings and forests and that kind of thing. So the ability of the Earth to reflect the light away from the Earth is also a contributing factor in addition to what the trace gases are giving us. And this is basically this basic physics. I'm sort of summarizing what you would take a course for in atmospheric physics. So what we've been experiencing, according to the IPCC, this is Michael Mann's temperature projection over the last 1,000 years, give or take, and it's called the hockey stick. You turn it sideways. It's, I won't say anything bad about the Leafs just because Joan would yell at me. But this has nothing to do with the Stanley Cup playoffs. This has to do with the fact that things are warming up substantially. And this was projected by the original studies that were done when I was taking atmospheric physics at the University of Toronto and University of Windsor. We were projecting that this was going to happen. This is in fact now started to happen. And it's basically looking at the amount of carbon dioxide and the Earth's temperature, and they seem to be in lockstep. And so we've got lots and lots of evidence that shows that. And make this, here's the temperature connection and the CO2 connection. As the CO2 goes up, and this is the last, this is the Pleistocene, running about, what is that, about 800,000 years. And we've had basic sawtooth temperature ice ages. We've had, I think they've counted 17 individual ice ages over the last 3 million years. This is at 800,000 years because that is the oldest ice core that we have, and that comes from Antarctica. The eastern Antarctic ice sheet is quite stable in terms of its movement, so we get very old ice, and we drill cores down, and we pull the cores up, and we can measure what the atmospheric state was, and so we get to determine what the temperature was, as well as the atmospheric makeup. And we coordinate that with other the things as well. So the global average temperature in Antarctica and in the globe work in lockstep. We actually see that things were much colder 20,000 years ago, but then again, 120,000 years ago, they were much warmer. And at the peak of the last interglacial, temperatures were slightly warmer than they are now. The difficulty is how quickly we're changing things. That is where we're having difficulty adjusting. So there is a very important connection between CO2 and the temperature. So we look at ice cores, we look at sediments. In Greenland, it's about 120,000 years old. It's the second largest ice sheet in the world, and it's on our doorstep. And we're going to talk about its effect on us as well. Antarctica is, we've got ice cores that go back about 800,000 years. Then we have various proxies. We look at the ocean sediments, like we can drill down into the ocean and the sediment falling through at a consistent rate. That goes back hundreds of millions of years. But when we go back hundreds of millions of years, the error bounds become bigger and bigger. So the further back we go in measuring things, the less certain we are as to what we are measuring. And so we look at the different types of measurements supporting each other. What do they support? What do they not support? And for the most part, they're all there. In terms of supporting each other, there are notable differences though. Tree rings, we're looking at hundreds of years to thousands of years, and that depends on the age of the tree. The oldest, I think, are bristlecone pines, and we do core sampling, and there are some ancient trees that have not, on Banks Island, they have not fossilized. They're from the Eocene. They're some 20 million years ago. And during the Eocene, we had swamps up in the Arctic. And there were trees growing there, and there were crocodiles and hippopotamuses that lived up there, even though it was 3 to 4 months of darkness. So we actually can go back to those tree rings as well. And we use carbon-13 and carbon-12 to date those things. And then we look at corals, dinoflagellates, tens to thousands of years, and then ocean water isotopes. Deuterium plays a role. So you wind up with I guess it's HD16O. So the oxygen has a deuterium instead of a hydrogen, and we can date things up to about 100 million years, maybe even more, as far as the climate goes. So those are proxies that help us in the measurement of what's going on. The oceans and the water, this is the critical interface. Most of the heat that is absorbed goes into the oceans. If we looked at the albedo, you'll find that liquid water has a very low albedo. It absorbs almost all the sun's radiation that falls in it. So 85% of all the heat that is absorbed happens in the oceans. And the specific heat of water is so important. Am I in the way? I see you trying to look. Okay. It absorbs an enormous amount of heat. Actually, going back to the Eocene, if we looked at the temperature profile of the ocean, it was actually 10 degrees Celsius at the bottom of the ocean. Right now, the temperature at the bottom of the ocean is roughly 2 to 4 degrees. So you can see there's a huge energy sink that happens there. So the oceans absorb so much of the sun's radiation, and then it plays into the El Nino, La Nina phase, which we'll get into. And the specific heat of water, it takes a lot of energy. Anytime you boil a kettle, it takes forever. And if you watch it, it never happens. So the amount of energy that's stored in the water is crucially important for a number of reasons. Again, we'll get into that. As the temperature of the water goes up, its ability to store gases changes. It actually goes down. So it outgasses all kinds of gases as the temperature of the water goes up. So you really don't want to have that happen, because you wind up with oxygen-starved areas, and you outgas things like sulfides, hydrogen sulfides, and they're very bad. Actually, they may be related to some of the massive extinctions that have happened in the Earth's past. So ocean water, you can see steam switching over from liquid water to vapor takes, that change of state requires a lot of energy. And the same thing, switching over from ice to liquid water and vice versa, takes a lot of energy. So it's a storage, it's a battery mechanism. Water is a perfect battery. It actually convects, it absorbs the heat in the tropics, and then as it moves through, if you look at the Gulf Stream, The Maritimes gets 25% of its total heat budget, 75% from the sun, 25% from the Gulf Stream. So we get an enormous amount of heat. I'm going to stop. Any questions so far? I said no snoring. That is a good thing. So, yes, please.
Ozone. That's bad. Ozone, when you go to a hotel and there's a smoky smell, they put an ozone machine in. How does it work? How long do you have to let the air clear out or settle, whatever, to not breathe in ozone that's harmful?
Okay, the question is, how long does it take for ozone to not be harmful if you breathe it in? First of all, it depends on the amount. Tiny little amount isn't a bad thing, but if you're looking at smog events and air quality events, then you can have fairly high ozone levels. Ozone's very reactive. It's O3 and it doesn't like to be O3. It wants to be O2. And the bond between oxygen is very, very strong. Oxygen is the second most reactive element in the periodic table. So its bond is only slightly less than fluorine. And if you breathe the mouthful of fluorine, it would rip apart all your tissues. So I wouldn't be too worried about the hotel kind of thing. If you can smell it, well, that'll dissipate fairly quickly unless they're manufacturing ozone or something like that. So that answer it? Yes.
Will we be able to access the things that you're showing on the screen?
Yeah, I think they're part of the, are they part of the lecture?
Will be recorded as a YouTube video.
Yeah, so it'll be recorded. So what I'm talking about, you'll be able to see. So,
Seeing it in person?
yep,
Okay.
yep, you'll see my face there as well. There are downsides to everything. So here's the flow of water that we're really concerned about. In North America and Europe, we depend on the Gulf Stream. And one of the effects of the climate crisis is that the Greenland ice sheet is melting to the tune of between 300 and 500 gigatons of ice a year. Like that's an enormous amount. But considering that there's 1 million cubic miles, 2 million cubic miles of ice, it's going to take a while for all of it to melt. At current rate, probably 500 to 10,000 years, depending on how hot it gets. So without the Gulf Stream, the temperatures here would be the same as Moosonee on southern, northern Ontario kind of thing. We'd have very, very harsh weather here. The Gulf Stream really moderates things. It provides us with an enormous heat budget. The problem with the Greenland ice sheet melting is that it sends out fresh water and it is less dense than the water coming up in the Gulf Stream and it caps it. So the heat coming off the Gulf Stream goes back into the ocean and it doesn't get into the atmosphere, which we depend on. So it destabilizes things. We don't know enough yet about how much of a destabilization it is. The ocean feedback, I mentioned El Nino and La Nina. Okay, so this happens in the Pacific. It's the central Pacific. So the Pacific is huge. It's if you turn the Earth a certain way, all you see is the Pacific Ocean. You don't even see Asia or North America. It looks like the Earth is entirely ocean. It's also a deep ocean. And what they noticed, the fishers in South America used to go out to some of the islands in the Pacific to collect guano, which was a fertilizer that was provided by the seagulls. And there were hundreds of thousands of tons of this fertilizer, phosphates that they were getting, that they were using for agriculture. And the fishers noted in Peru that at certain times the ocean was cold and at other times it was warm. And it ran in cycles. And this feedback mechanism was thought to be a local phenomenon until climatologists got involved, and they found out that there seemed to be certain climatic trends that were in lockstep with El Nino and La Nina. So what are they? They're part of what's called the El Nino Southern Oscillation. And so El Nino is a warming of the Pacific. So warm water comes up and it interfaces with the atmosphere and it disrupts climate. So you wind up with the monsoons in India being disrupted. You wind up with hot temperatures in Australia. You wind up with fire tornadoes. I don't know if you remember the last time we had an El Nino, they had tornadoes that actually happened from the forest fires that were happening in Australia. And it leads to more intense storms in some places and then droughts in others. And the droughts happen in the Sonora Desert, which pushes up into southern Canada, into Texas. Maybe that's why it leads to extreme politics, but that's another story. Anyway, so it disrupts weather patterns, makes life miserable for a lot of people. And we first started talking about it when Bill Hare, who was a climatologist at the University of Toronto, was giving talks about El Nino back in the 1980s, and the Sahel was being gobbled up by the Sahara Desert. By the way, the Sahara Desert is a recent phenomenon. It's only been there for about 7,000 years. Up until then, there were lakes and trees and crocodiles and things like that, and it's just dried up recently. And it's an interesting phenomenon when you start taking a look at the various effects that the atmosphere has on geographical regions. La Nina is the cold upwelling. We've had an unusual circumstance this last 5 years or 6 years because we have had 3 back-to-back La Ninas happening. This usually doesn't happen. And this is an unusual circumstance. So the temperature will be colder. And again, it has an effect worldwide. In Canada, we wind up with cooler winters, which has not been the case in spite of the fact that we've had La Ninas the last 5 or 6 years. And you wind up with near record-breaking snowfall amounts, that kind of thing, which again didn't happen. So it tells us that we have a lot to learn about these phenomena. So these 2 phenomena are things that we're really looking at, and they have dramatic effects for us to a certain degree. But if you're living in Africa, if you're living in India, or Australia, or the southern area of the Indochina region, you have dramatic effects. Let's talk about the cryosphere. This is the thing that's, I think, we notice the most in Canada because we are a northern nation. And that coupled with Northern Europe, we're really concerned about what is happening. I'm just looking at my watch here. We'll take a break in about 5 minutes, and then I'll continue on. So we're looking at Arctic, Antarctic, and mountain ice. And most of the ice is tied up in what's called the Eastern Antarctic Ice Sheet, EICE, I guess. And it holds about 80% of the world's fresh water. The next biggest one is Greenland. And then the next biggest one is the Western Antarctic Ice Sheet, or WAICE. And you can see a picture of those there. So in extent, the Arctic, because of the albedo, is probably more important because it's part of the Northern Atlantic and it affects the heat budgeting based on how the Gulf Stream flows, the conveyors that give us a lot of temperatures that we need. The Greenland ice sheet is, if it were to melt, would give us 6 meters of water, about 20 feet of water, and it's in the process of melting. As I mentioned, every time I talk about it, the amount of ice that's melting goes up. So it's between 500 gigatons and 800 gigatons, which giga is big, lots, and it is like almost 1 million square miles, 864,000 square miles of ice for the most part. Antarctica, composed of 2 sheets. This is what Antarctica would look like if it all melted. You can see it's just a series of islands, kind of a large continental mass. That little nose sticking off to the left, that is the WAIS, or the Western Antarctic ice sheet, and then the stuff off to the right, that is the Eastern Antarctic ice sheet. And you can see how much ice there is. 60 meters of water, 200 feet, if and when. And it's now a case, we thought it was stable and actually accumulating snow and ice, but it turns out the snow budget is such that it is not accumulating ice in the Eastern Antarctic ice sheet. If you look at the Eastern Antarctic ice sheet, it is kind of like a bowl. The ice has depressed. The ice is actually up to 15,000 feet thick. So when you're standing on top of the ice in the Antarctic or in Greenland, you're actually standing in the middle of the troposphere. You're standing on a mountaintop of ice. So it has pushed the continent down. So there we go. That is the end of the first part of the lecture. And any questions before we? Yes, sir.
Richard, I was just wondering, in the next number of years, we may be able to stop spewing stuff out into the air and reduce some of our environmental disasters that way. But if the oceans keep heating up, and I know some of it is probably natural, but is there any way that humanity would be able to roll back some temperatures of the ocean by change?
You're talking, so it's a question that basically, if I can paraphrase it, is talking about geoengineering things so that we can get rid of some of this stuff. Boy, that is a loaded question. And it's loaded because there's a lot of controversy. The scientific community and engineering communities are divided. There are a lot of engineers that say, we would like to tinker with things, and we want to use various methods to lower the temperature to actually change the damage we've done. Who gets to make that decision? Do the people in Africa make that decision, or do the people living in Ottawa and Washington and Copenhagen?
I think that if the desire is there, we could as a planet.
The question is, could we? And there's, I remember talking, I'm going to name drop here. I was talking with David Suzuki, and this is kind of a, I call it the Suzuki effect. For every engineering principle, any engineering that you do, there is an unexpected result. And it happens like little green apples. They just pop up. So you think it's going to do one thing, but it actually does something else. And then you're starting to do whack-a-mole, trying to fix these things. So the easiest thing is not to do it. As my mother used to say, don't do that. Anyway.
About doing something that could reflect the sun away from the planet, from away from the clouds.
Yeah, so it's like whose ox is getting gored? Who is going to receive the benefit and who is not? Is this going to be a private enterprise, or do governments get together, or do scientists make the decisions? Scientists don't make the decisions; they just provide the information.
Private enterprise twice in a row now in the last week, and cracked two rocks.
I think you've hit that on the head. Oh my goodness, I'm looking at myself. I got to get away. Housekeeping. Two housekeeping announcements. The first is, if you have a question, stand up so that the microphones can grab your question. I will repeat the question, but do stand up so we can project better for the microphone, so the folks at home can hear and everybody can share in the question. The second thing is, at the end of the lecture, we need to put the chairs away. So if we could have some help doing that, that would be terrific. And the third thing is we accept donations for the staff and all that kind of stuff. It's spelled Z-U. Anyway, here we go. So this is going to be lecture 2. So one of the important constituents in how the climate has evolved has to do with plate tectonics. And the reason that we are in the middle of this last 3 million years, it's called the Pleistocene, have been a series of ice ages where the ice has advanced and then contracted and then advanced. And as I mentioned at the start of this, it's happened about, I think now 17 times we've been able to figure that out. And we've been the beneficiaries of it here in that we've got no topsoil in Nova Scotia for the most part because of the ice. It's all pushed into Maine or the States. The States always gets our good stuff. Anyway, so plate tectonics. 100 years ago, we were trying to figure out why certain sediments were showing up at mountaintops, why certain fossils looked like they'd been at the bottom of oceans, and it seemed like the continents were moving. And so Alfred Wegener was the first one who coined this. He started talking about continental drift. And when I went to school as in the 50s and 60s in grade school, we talked about in geography class that the continents appeared to have drifted. And if you look at North America and Africa and Europe, they kind of fit together like a jigsaw puzzle. But when the physicists came in and did an analysis of it, it was impossible to have the continents drift through, rock can't drift through rock. So how does this mechanism take place? How does this work? And we started to get the idea that the continents were in different places. The continents are basically solid froth. If you compare the average density there is about 5.5 grams per cubic centimeter. And if you look at the rocks that we have here, if you pick up a rock, it's between 2 and 2.5 grams per cubic centimeter. So the continental rock is really lacking in density compared to just about the rest of the earth. So we started looking at the interior of the earth. And the way we did that was through earthquakes and through mining, and that can't go very deep mining. I think the deepest that we drilled was the Moho project back in the 60s. And I think we got down to about 13 miles and then it just collapsed. And it just got more and more difficult because of the pressures and the heat and all that kind of thing. But what we discovered is that there's a mechanism, that the mantle and the core contribute to that mechanism. And there's a combination of molten and semi-solid material that's moving and driving things. And so we've got a bunch of jigsaw plates that are put together, and you can see them here on this diagram. So we live in the North American plate, and then there's the Eurasian plate, and where they're stitched together, there's subduction and zones where one plate is going under another, and that's where you wind up with mountain ranges, and things are changing. The Atlantic Ocean is expanding, I think, at about 2 to 3 centimeters a year, so flights take longer to get to Europe this year than they did last year. And over the course of millions of years, the positioning of the continents is different, and that affects the ocean currents, and that affects the heat flow, and that affects the climate. In addition to that, the Earth also wobbles because of this molten. It's kind of like if you take a solid top and spin it, it spins pretty good. But if you look at, or spin a hard-boiled egg versus a non-cooked egg, they spin differently because the interior has an effect on how the Earth spins. But even so, there's a wobble to the Earth. And that's called a Milankovitch cycle. And affects how the sun's radiation comes in as well. So plate tectonics plays a role in climate change. And right now, for the foreseeable future, it looks like the continents are stuck for the foreseeable future. They're not going to be moving very quickly. And okay, there we go. The mechanisms are on this time scale of millions of years. During the Mesozoic times, when the dinosaurs were around from the Triassic through to the Cretaceous, about 200 million, 225 million years, there was basically no Atlantic Ocean. So in that time frame, the Atlantic Ocean is spread out. And as I said, it looks like a jigsaw. So the Milankovitch cycles are even more complicated. These are cycles that are related to a spinning top, and the Earth's pole does this kind of thing, and it points to a different star. Right now, it's basically pointing at Polaris, which is the tail of Ursa Minor, which is the constellation or the Little Bear, and it's just a degree off. So the North Star, Polaris, just sort of does a little circle. The other stars travel around it, but in 12 or 13,000 years, there will be another pole star. And there is no pole star for the Southern Hemisphere. There are no stars close enough. So what we've been able to relate is how the Earth is tilted into the sun has an effect on its temperature. In the Northern Hemisphere, during the summertime, we're actually further away from the sun than we are in the wintertime. And it's the directness of the sun's insolation on us that is the determining heat factor. So Milankovitch was a Serbian researcher about 100 and some odd years ago, and he was able to relate all these different, the closeness of the Earth to the sun, the oblateness of the Earth's orbit, the oblateness of the Earth itself. It looks like kind of a squashed. The North Pole is actually 26 miles closer to the center of the Earth than the equator is. So you can see the effect that that's having on the actual structure of the Earth. So the Milankovitch cycles and plate tectonics do have an effect on climate, and it's a major reason why we're in the middle of this ice house this last 3 million years. We started to drift into it about 35 million years ago during the Eocene when things got a little bit cooler. So today where we stand, according to AR6, human activities, principally, now that we're looking at getting done with the physics of it, we're going to talk about what all of this is telling us. So we have raised the temperature between 1815 and 2020, about 1.1 to 1.2 degrees. And global emissions have continued to increase. The only time that we have a decrease is when we have a disease that limits industrial output. Like we did notice a little dip in 21 where the emissions didn't decrease, they plateaued. But we've continued to increase, and the AR6 is telling us we've got to do something yesterday, like we got to do something now. So we are looking at, if we're to mitigate, the goal is to stop things at 1.5 degrees Celsius, and then by stopping it, lowering the carbon dioxide from roughly 421 or 422 parts per million back to 350. If we get back to 350, we will slow down the pace of change, and we can adjust better. And it's better for the ecosphere, plants, animals, and us will adjust much, much better, but we've got to do it now. So land use, lifestyle, patterns of consumption, productions across regions, all that kind of stuff has to be taken and factored in. Widespread and rapid changes have occurred in the atmosphere. We notice the temperature in the troposphere is 1.1 degrees warmer than it was, let's say, in 1850. In 1850, I think we were at about 280 parts per million. Right now, we're at 420, roughly. And when I started complaining about climate crisis, we were at 380. So it tells you that we've we just don't listen. And the policies that we have in place right now are insufficient according to the IPCC. And the Intergovernmental Panel on Climate Change is a group of roughly 3,000 climate scientists. So this is the distillation of the papers. It's important to realize that it's not an opinion. What this is a summation of the scientific studies. So a scientific study comes out and it tells you one thing, and then another one comes out. We're looking at about 30,000 individual papers that over the last 30 years have gone into the making of the IPCC's reports over the last 30 years. And they've been uniform in telling us that we need to do something very quickly, and we've squandered a lot of time. So we're now at the stage where we have to do something very, very quickly, and maybe even talk about geoengineering, which was brought up just before the last break. So the math of climate change is absolutely unavoidable. It is based in scientific literature, and it is based in scientific study. And if you ask me if climate change is happening as a researcher, I will say, according to the studies, it looks like it is happening. And it's not based on my opinion. It's a distillation of all the scientific studies. In 2019, there were roughly 5,000 or 6,000 specific climate papers published that supported the outcome that climate change was happening. There were 8 papers that disputed that. And out of those 8 papers, out of 5,000, we found that half of those papers were spurious. They were just wrong. And the other 4, they found that they were not wrong, but they indicated that further study needed to be done. So they called to question whether the climate crisis was happening. And so the overwhelming body of evidence is that the climate crisis is happening. So the main tipping points right now, we're looking at the boreal forest. It is an important carbon sink. When a tree grows, when you want to talk about geoengineering, that is the perfect mechanism for taking carbon dioxide out of the atmosphere and sticking it into carbon. And so if forests are healthy and exist, you have this great carbon sink. It is in a stable situation where the photosynthesis happens in the leaves or the needles of the forests, and it goes into the carbon of the tree. And as long as the tree is alive, or the tree is not burned, or the tree is not utilized in some way so that the carbon gets back into the atmosphere, it's a carbon sink. So the health of the boreal forest, we have the largest extent of forest in Canada, in the world, and we're rapidly eroding it. So that's one possible tipping point. Another one, as we touched upon, was the ENSO, the southern oscillations of El Nino and La Nina. They change in magnitude. They're getting worse. They're getting more protracted, like we saw that with 3 back-to-back La Ninas. The dieback in the Amazon rainforest, it is now seen, the studies are telling us that it is unstable. It's untenable for the health of the rainforest to continue at the current rates of deforestation. And the previous regime, before Lulu was elected, had increased the deforestation. We're now at the point where the Amazon rainforest could completely collapse if it gets past a certain point. It's the same thing as the boreal forest. If we take too much down, it becomes a significant problem for the carbon uptake. The melt in the Greenland ice sheet, that is a really important for us and Northern Europe. If that happens, we're going to go into a mini ice age here. which is some denialists have said, well, if that's happening, that just shows you that climate change is not real. It's not happening. But that's just a short-term thing until the ocean heats up and we wind up with the same mechanism. And then our climate takes off on steroids. So we'll actually lose that heat that we get from the Gulf Stream that provides 25% of our heat budget. We're looking at the African greening, the southern part will benefit. There's an ozone hole over the Arctic that will also play a part. It will continue to increase, and you're looking at the Western Antarctic ice sheet and the changes in the temperatures of the ocean profile. That's a problem. And then you're looking at the Indian monsoon being unstable. And then there's the permafrost, where all that carbon has gone into the peat bogs in Siberia and in the tundra. They will start to release methane. And when the ocean temperatures change, we have methane clathrates, which is semi-solid methane at the bottom of the ocean, which will then start to vaporize and bubble. Everybody depressed right now? Okay, so these are the main tipping points. Yes.
Monsoon shift.
Okay, so the question, you were supposed to stand up. Yeah.
A monsoon shift.
Okay. Boy, some people don't listen, do they? So thank you, Joan. The stable winds that occur seasonally when the climate is in its normal phase leads to a group of winds that blow off the Indian Ocean and provide the monsoon rains. They're very, very important for agriculture. And when and they're almost like clockwork. They almost start on a specific date and stop on a specific date. And so they become chaotic. And some years you don't get the monsoon, you wind up with a drought. And if your agriculture is dependent on it, and of course, in that part of India, they've lost a lot of the jungle there. If it's chaotic, they're not getting the right weather patterns and they're getting different types of temperature profiles. And that is a destabilized. So populations will move. Because of the switches in agriculture based on the monsoons. They really do depend on the monsoons for the agriculture. And we have what are called dynamic and stable equilibrium points. And this is an important physics thing. Think of a swing. You take a swing and you push it, and it comes back again. And you push it, and it comes back again. That is called a stable equilibrium. And our climate is an oscillatory occurrence on the Earth. And so you push the temperature a bit and it has a predisposition to go back again. You put a little more carbon dioxide in, the ocean uptake happens. You get more snow in in the Antarctic. That lowers the temperature a bit, that increases the ice. And so it's a stable equilibrium point. Those types of stable points we're not too concerned about on the average, as long as you're not pushing too hard. It's like pushing the swing too hard, and then the swing breaks, or the swing goes around, or something else happens. There are also dynamic equilibrium points. These are the ones that are very worrisome. Think about being on the top of a hill. You're balanced on the top of the hill, but you move just a little bit. What happens? You accelerate down the hill and you don't come back to the top of the hill again. And those are called dynamic. And we don't know which ones are dynamic and which ones are stable to the degree that we'd like to know. So we're still learning about this. And when the science changes, it changes our outlook. So these are the two types of stable points that we're looking at that relate to the tipping points. And so when we talk about tipping points, how much Greenland melt can we take before it's irreversible? How much deforestation can we take before it's irreversible? Human population, how much agriculture, how much change in albedo can the Earth change before it's not switchable? It's like a flip of the switch, and then you have to work really hard to switch it back again. So those are the things that we're trying to determine right now. In the last 50 years, This is the heat budget of the Earth. And you'll notice there's only one, blue is cooler. You don't see much of it. And you see it in the eastern Antarctic ice sheet. And it looks like some parts were cooling, but that has now started to change. The big change is happening in the Arctic, in the ice sheet in the water. And the reason that it's happening there is because the preponderance of ice in the Arctic is in the Arctic Ocean. And it is floating. And so as soon as it melts, it changes the albedo of the ocean. The ocean uptake of heat goes up dramatically. And of course, that's where you wind up with the greatest manifestations of the climate crisis. That's where the temperature is most profound. And we see that happening in all Arctic regions, and it's uniform. And then you look at other places, Australia is getting kicked. And you can see Canada, the northern part of the Northwest Territories, they're getting massive uptakes in permafrost melting, that kind of thing. They're noticing that in Siberia as well. They've got an unusual occurrence in Siberia of methane explosions, where they wind up with methane domes and they actually explode upwards. And so you wind up with a crater that can be hundreds of meters deep and hundreds of meters wide. And they couldn't figure out where these things were coming from. But that is in the permafrost, where all the methane is coming up and it ignites. And they're getting lakes which are bubbling up methane. Okay, enough of this. So we have human and natural drivers coming together. The natural drivers are the ones we talked about in the last hour. The basic physics of the atmosphere, the weather, the climate, that kind of thing. And the human drivers have now gotten to be as big as the natural drivers. Often you'll hear the argument saying, well, you know, a volcano will throw up as much CO2 and greenhouse gases as all the industrial activity of the Earth. But if you average out the natural drivers, you talk about the Milankovitch cycles, you talk about the plate tectonics, you talk about the biosphere uptake, that kind of thing. Well, that averages out over the years. You get maybe a mini ice age in Europe, maybe a greening of the Sahara based on certain Milankovitch cycles. But what's really changed are the human drivers. And we are a carbon-intensive economy. If you look at what has been driving us, it is fossil fuels. And the trouble with fossil fuels is they're so gosh darn convenient. They're accessible. They bubble up all over the place. I mean, you look at the La Brea tar pits, you look at natural gas, you look at the Middle East is just bubbling over with oil. You drill a hole, you don't wind up with water, you wind up with oil. And it has a lot of energy and it's easily refined and it's got a lot of uses and it's convenient. The internal combustion machine is probably, there must be 2 billion of them on the face of the planet right now. We're talking 2-stroke and 4-stroke engines and almost 1 billion cars. And then you're talking about travel. Nothing else compares to the convenience of fossil fuels. And our entire civilization, our technological civilization, has rested on fossil fuels. And what's not to like about them? You know, we've gotten more efficient, we've got hybrids, we've got airplanes, we've got economies that are based on it, we've got petrochemical industries. So they're part of the human driver of what goes into the atmosphere, and they're addictive. So we don't look for other energy sources. We don't look for better batteries. We don't look for hydrogen or anything like that. Fossil fuels have been uniformly the driver of our society. It's the reason we have technology. I look at my clothes. I look at how I got here. I look at our building. All of that is the result of the fossil fuel industry. However, the effects that we've been adding have exacerbated things. We look at wildfires. We're looking at wildfire tornadoes. I had never heard of anything like that before until I saw it in Australia. Droughts, Lake Mead is now down I don't know how, every time I look at it, it's worse. Although with the ocean, not the atmospheric rivers that have happened in Florida, some of the drought has been ameliorated, but generally speaking, it's not enough to end the drought. So the southwest of the Sonora Desert Museum, pushing up into Saskatchewan, that is still in a drought condition, and Texas and New Mexico and Nevada. And then you're looking at coral bleaching. The ecosystem of the corals are irreplaceable. They're on par in biodiversity, on par with the jungles of the Amazon. So they're very, very important. And that's where our biosphere evolves. And that's where our biosphere connects with us. And if we lose our biosphere, we're starting to lose that pyramid which supports us. And so you look at the biosphere as supporting us, you start whittling away at the support network, it will topple at some point and come back to a dynamic equilibrium as opposed to a stable equilibrium. So CO2 emissions by source, this is how it tops out. You look at the fossil fuels, gas, oil, and coal. There's our fossil fuel footprint. That's what we use. China has now gone back to building lots and lots of coal-fired plants. So anything that stops us using fossil fuels is good. So the other and land use has an effect, but it's just a small fraction of what we are getting at a fossil fuel. So right now, the big message is fossil fuels bad. If you can get off that somehow, that's good. Global tree loss. We love our forests, and it continues to go up, especially in the tropical and subtropics. We're increasing our use of boreal forest, that's Canada. Like we're mulching so much. I mean, I don't know if anybody's had a chance to drive through Northern Ontario, try to get from Sudbury to Thunder Bay. It's like rocks and trees and rocks and trees and rocks and trees. You drive for a day and you're still in Ontario with rocks and trees, but we're mulching it. We're taking all of those forests and we're changing it into paper. We're changing it into lumber. We're changing it into flooring. And that's not a good thing. We've got to learn to stop. The tropics are probably in worse shape than our boreal forests because of the systems of government and the level of corruption. Sea ice loss. This is the one that's scary for us, because with sea ice loss comes the change in the ocean temperature. You change the ocean temperature, you talk outgassing, you talk changes in albedo, you talk about changes in the absorption in how the oceans take in the sunlight of the earth, and you change the greenhouse effect. You change it into a greenhouse crisis. So ice loss is really important. We're at the lowest levels that we've ever recorded for Arctic ice. And when that happens, it's only a matter of time before we start looking for the oil under the Arctic Ocean. There are 150 billion barrels of untapped oil in the Arctic Ocean. And somebody wants that because there's money to be made. And we're going to be talking about the effects of money on that. So sea ice loss is really important. And we're starting to notice it as the ice calves off of Greenland and the size. I'll be interested to see what happens this year and next year with the Arctic ice, how low it will go. The La Nina phase has meant that we haven't hit the historic lows in the Arctic ice that we recorded in 2012. We've been way below average, but slightly above. 2016, I think, might have been almost as low or lower than 2012. I have to check the maps on that. But we probably will have an all-time low of Arctic ice. So why is it important to do something now? I mean, the Earth has been warmer in the past. So what happens if at the end of the century, it's 4 degrees warmer as opposed to 1.5 degrees warmer? Well, this tells you the temperature profile. It's on average. So that means the Arctic will have no ice. And then we're on the threshold of something called a runaway effect, where everything that we do will not stop it from increasing in temperature until something happens, either with the positioning of the continents or volcanic outbursts or something like that, to stop the increase. When we hit 4 degrees, a lot of the methane in the ocean will come up. Methane is 60 times, roughly, depending on how you measure it, the greenhouse gas of carbon dioxide. And in addition to that, you'll be releasing a lot of methane and carbon dioxide from the permafrost, which again, you can see the hottest places are the Arctic, and that's mainly related to the albedo. With no ice in the Arctic Ocean becomes just like the Northern Atlantic. And the ice not being there means that the global temperature increases, will continue to increase, and the flow of the ocean conveyor, which connects all the oceans, will be transporting even more heat into the Arctic. And we'll wind up with a 4 degrees rise, which means that by the end of the century, we could have the possibility of 3 meters more water. That's 10 feet of water globally. So all coastal areas. And if you've got swampland in Florida, you've got ocean bottom in Florida. And to tell you the truth, with the political situation there, sometimes I think nasty thoughts that it couldn't happen to, never mind. I'm supposed to say nice things. Another thing that's going to be affected is soil moisture. And with the temperature going up, that means that the evaporation rates increase and moisture in a lot of places. And you can see what happens in South America, what is traditionally a rainforest. It's a dry area. Look at North America, all the way from Mexico up, well, actually from central. What happened to the Mayans? They lost their civilization when their agricultural processes couldn't deal with a massive drought. It was a mega drought that happened 1,000 years ago. And before the European colonization, they had a civilization that was on par with the Roman civilization in terms of sophistication. And it all disappeared because of it. So soil moisture means a lot of crops cannot be grown. If you look at what's going to happen to Southern Europe and the Mediterranean, it's going to be catastrophic. If you're going to Italy or Greece, you're going to be going into sweltering heat. The Middle East will be unlivable. I'm saying that to my wife right now. Going to Italy at the end of July and the beginning of August is going to be a treat in terms of heat. It's good luck. And some parts will get wetter. You'll wind up with certain areas getting more moisture with the change in climate. But if you look at the northern regions, it doesn't matter because there's not much soil there because of the ice ages. So you might have a little bit of Arctic tundra there, but it's peat. So it's not very rich, and most of it has been pushed down into the southern areas. So even if the soil temperature, it gets wetter there, it's not holding a whole lot of water. So this kind of is a map that distorts things just a little bit. So sea level rise. Now this should interest us. When I was a counselor, I was always amazed that the planners would come in and say, yes, we've taken into account sea level rise. We're expecting that it might go up by a foot or 2 by the end of the century. I go, excuse me, those are best case scenarios. And we are accelerating sea level rise. And if you look at Michael Mann's hockey stick, temperature and carbon dioxide increase, it's directly relatable to sea level rise. And with Greenland on our doorstep, we're going to be benefiting. Right now, I'm looking at studies that are saying, yeah, get used to 3 meters of water. And if you take a look at the historical building in the Maritimes. We have a lot of buildings that are 100 years old, close to the waterfront. It is not hard to imagine certain buildings being built along the waterfront that are going to have in-ground pools, and there'll be ocean pools. So that is of concern. You look at the satellite data, projected ice melt. Well, and I'm thinking that maybe at 3 meters, we're being a little optimistic. So we're also looking at ecological collapse. I hate looking at this picture. It breaks my heart. You look at pest increases, like we talk about invasive species. We now have 5 species of mosquitoes that have moved north. 50 years ago, we only had 2 species. Now they're moving north. So the mosquitoes that are biting you in February, you get a different species in November, and they're there. And creatures that have adapted to a certain lifestyle cannot. So the pictures tell the story. The bleaching, the forest fires, the invasive species attacking our ecosphere, from plants to insects, that kind of thing. So we're also looking at extreme weather. That's a cross that we are going to have to bear. The storms are going to become more frequent. That's winter, spring, summer, and fall. The hurricane season is going to become longer. And where things like tornadoes didn't happen very often, we might see them with severe thunderstorms. So you wind up with supercells, which will generate these things. We're not prepared for it. We're not building for it. And so extreme weather, you look at winds. Winds are a great equalizer. When we have sweat winds that now clock out at 160 kilometers an hour in Cheticamp, and you've got the wreck house winds in Newfoundland because of the Bernoulli effect, Venturi effect, equalizing pressures. But that's going to happen more frequently. You're going to have to change your building codes. You're going to have to change how you weather things for flooding. So you're looking at floods, and with floods come invasive molds. So you get a flood in the basement. It's not just getting the water out and the damage, but then the mold comes in. You're looking at health effects. You're looking at other opportunistic creatures coming in. And all of this goes up as the temperature goes up. If you hit 4 degrees, I mean, you're talking an increase in heat waves by a factor of 40. So I have a heat pump in my house. And one of the things that I'm really grateful for is that it provides air conditioning. Well, 35 years ago, when I came to Nova Scotia, I didn't have to worry about air conditioning. And now we talk about it. So these are the changes with extreme weather. So it's heat, it's wind, it's drought, heavy rains. The heaviest rain ever recorded, and to give you an example of a possibility, happened in 2020 in Mumbai, in India. They got 5 feet of rain in 12 hours. 1,000 people died. I'm just amazed it was only 1,000 people. But that kind of rainfall is possible. They got just a couple of weeks ago in Daytona, Fort Lauderdale area, they got 2 feet of rain in 24 hours. And those types of rainfalls are unprecedented. So can you tread water? Environmental migration is another thing that we haven't considered. We have 40 million people living in the Caribbean area. 40 million. That's more than the population of Canada. Where will they go as things become worse? And they will get worse. More. Who wants to live in Hurricane Alley? And really, they start off the coast of Africa, and what do? They shoot over to North America, going through the Lesser and Greater Antilles, and hit Cuba, hit Jamaica, hit Florida. Not enough, and then move off. just politically. Anyway, So environmental migration is going to be a big factor. We're not taking that into account. Agricultural changes. We have to start learning how to grow things better. Can we grow things vertically? Can we grow things in greenhouses? Can we grow things differently than we used to? We have vast tracts of land that use a brute force method, pump the water out of the ground and flood great areas that have, oh my goodness, it's almost that time, witching hour. So agricultural changes are going to be happening. Tidal flooding, tides are going to get higher. And so you're going to get tides coming. This is a picture of Venice, which is, yeah, underwater because of the tides. And coupled with storms, you wind up with tidal surges, storm surges, all that kind of thing. Moon surges, whether the moon comes in at high tide, neap tide, that kind of thing. Storm intensification, seeing storms with winds that exceed the category 1, category 2. Had one been 10% stronger, this is something that they don't tell you, 10% stronger in terms of winds. The destructive power of the wind goes up as the 4th power of the wind. So if it doubles, it's not twice as destructive. It's not 4 times as destructive. It's not 8 times as destructive. It's 16 times as destructive. So you have to build buildings. So storm intensification, we don't understand on a root level how important that is. And then, of course, heat waves. This is some of the heat wave profiling that happened in Argentina just a few years ago when they got a massive influx of heat. We're going to wind up with much more heat because of that. And so pathways are no climate policies. We're looking at 4 to 5 degrees. If we implement things, we'll peak. If we implement things right now, we'll peak in the next, before 2030, and then start to decline and stay at 1.5, but you can see the different greenhouse pathways. Bad news if we don't start doing something now. Energy consumption, well, again, our energy consumption continues to increase. It shows you that fossil fuels, big bad. Nuclear, not so, there's a good discussion to happen with nuclear as to whether, was it George Bush saying nuclear? I won't say that. Hydro's increasing, other are increasing. That's good news, but we got to get rid of the fossil fuels. Economic sectors, industry is something we have to rein in. They're the big bad. Land use plays a role, buildings play a role. Transportation is huge. That's bad news for us. Moving people from one place to another is as important as moving sewage or moving hydro or having water. Travel is part of our matrix of our society. You have to have it. So how do we do it? World rankings, red, bad, green, good. We're bad. Can you see? Okay, sorry. So look at North America. We have not learned. Total fossil fuel emissions still going, it's still way too high. If it's not going up, it's sort of semi-stabilized. Per capita emissions, it's the wealthy. You know, the top 10% emit 90% of all the fossil fuels. Canada emits as much CO2 as the entire continent of Africa with 1 billion people. Okay, so a child born here is going to consume in the course of that child's lifetime 60 times what a child in the Congo would, a Democratic Republic of Congo would consume. So we're the problem. I'm sorry. And then scientific versus public consensus. We still haven't got it. You know, the people that get it really well, but there's still a huge group of people out there that are indifferent to it and don't get it. And next week, 3 minutes over, sorry. Next week, it's paleo. Don't forgive me too much. I'm still talking. Next week is paleoclimate. So we're going to delve into what has happened in the Earth's deep past. This is really a favorite of mine. I love this. It gives you a sort of snapshot of what could happen, what might happen, or might not happen. So enjoy. Any questions? I'm going to stick around for a bit. If
I've taken about 5 or 6 courses through scans in the last, I guess, few years. I think this is the best one yet, and I got.
Thank you. Thank you.